Let's see. We are now at question 36 in chapter 10. Uh, Talon has some money she wants to put into a savings account, and she has two options. One option is 2% interest compounded quarterly. Okay, so the fact that it's compounding quarterly is important, right? Because that means we need to make four compound um, periods out of this 2% interest. So our equation is going to look a little different than it would if it was just compounded annually. Another option only pays 1.5%, but it is compounded monthly. If she wants to deposit the money for 5 years, which account is better? If she wants to deposit it for 25 years, which account is better? All right, so let's take a look at this, and we're going to kind of write two different equations to model each situation, and I'll probably use my calculator then, and we'll extend this out to see if we can figure out what would be better, um, either for 5 or for 25 years. So first thing I want to do is create an equation for option 1. Okay, so in this option, our model, let's see, so the thing is we're compounding this quarterly, so that means 4 times a year. So I have to take the 2%, which is 0.02 expressed as a decimal, and I need to, whoops, my bad, and I need to divide that into 4 different interest amounts. So this is going to be the interest, 0.02 divided by 4. It's going to be the multiplier will be, well, let's see, it'll be 0.005. So that would be 0.5%. Makes sense, right? 2% divided by 4 is 0.5%. 0.5% is the interest I'm earning per quarter. My multiplier, right? My multiplier is not that number, right? That's not spelled right. Multiplier is that number plus 1, right? If I was multiplying by 0.005, that would be decreasing, meaning 0.005 remains and most of it goes away each time. But my multiplier is going to be 1.005 for this situation. Now, there's one other thing that has to change. They do not talk about the amount of money, right? She says if she wants to deposit the money, right? She has some money, some money. They're not telling me an amount of money. And the truth is, it doesn't matter what the amount is, right? It could be $10, it could be $1,000. For the sake of argument, I'm gonna say I'll get the same answer regardless of this amount, but I'm just gonna say let's let us say she has, I'll say $1,000. That's kind of a nice number. She has $1,000. So if I was going to write the equation that would model this compounded quarterly, I would write y, the amount that she has, is equal to her initial deposit of $1,000 times 1.005 raised to the, now, I want x to be the number of years. So for me, x is how many years. If I was to just put an x right here, that would be number of quarters, right? Because if x was 1, remember this is the amount for 1 quarter. These are divided quarterly. This would be the amount of interest she would realize after 1 quarter. But because these are both different, and I want to kind of normalize them so I can think of them the same, I'm going to put up here a 4x. That means now x is a year. So if I put 1 year there, that's going to be the equivalent of multiplying by this number 4 times, right? That'll give me the 1, 2, 3, 4 times the hit with that. So that'll realize my 4 quarters for that person. Okay, so now we see this pattern here. Let's see if we can't do the same thing for option 2. It'll be easier now that we kind of see what's going on. So for option 2, for option 2, the interest here was 1.5%. Well, let me write that as a decimal though, so that'd be 0.015. 0.015. But instead of dividing by 4, this one says it's compounded monthly. So I'm taking that interest rate, this annual interest rate, and I'm dividing it by 12 to get 12 compounding periods. Now this number is 0.015 divided by 12. It gives me the number 0.00125. It's very much a smaller number than the 0.005 from the other option. And my multiplier for this situation, multiplier, is going to be that number plus 1, so 1.00125. So the other adjustment I have to make, right? So for this for option 2, y is going to equal this $1,000 initial deposit times 1.00125. But instead of raising this to the x power, which in that case x would represent months, and I don't want that. I want x to represent years for both of these. I'm going to raise this to the 12x power. So on this second option, right, when x is the number 1, that means that this thing would have went through 12 compounding periods. I would have had this 1,000, I would have literally multiplied by this number 12 times. Over here, when x is 1, I would multiply the 1,000 times this number 4 times. Now, for sure, this is a larger number, right? 1.005 is larger than 1.00125. But realize every single year, this one's going to be multiplied. This is going to be multiplied by that number 12 times over here. Every year it's going to be multiplied by it 4 times because there's 4 quarters in a year and 12 months in a year. So now our question is, now that I've modeled these, I need to come up with a way of looking at these two situations. And I think I'm going to go different this time. I think I'm going to use either Sheets or Excel. So let's grab those tools. So this is a nice clean open spreadsheet, and I know some things about spreadsheets. So the first thing I'm going to do is I'm going to set up this first column, and I'm going to call this column years. So I'll just click there and I'll type YARS, years, and I'll go, let me go no years, 1, 2. Now you don't keep typing like that. What you can do is, I think if I just click 2 of these things and I drag, nope. No, I'm not going to do that. What I can do is I can say, hey, the next one is always going to equal the one above it plus one more. So now that I've typed this cell as a formula, you can see this formula just says this cell that I'm at equals the cell right above me plus one more. Now I can just drag this down. Oops, not like that. Sorry, class. If I put my cursor here, I can drag this down. As then I do that, it's automatically updating this. Now, one of the questions was, what if it goes for 5 years? But it also said, what if it goes for 25 years? So I'm going to drag this down far. Well, now I'm up at 37 years, so that's more than I need, but that's okay. So those are my years. Over here, I'm going to call this one option 1. And then over here, we'll put option 2. By the way, if you've got your TI-84s, you can do something quite similar with that, right? You don't need to use a spreadsheet, but I think this is actually easier for me than doing it on a spreadsheet. Okay, so the formula here was, remember, this number stored in this box is going to equal x, right? So that's my x value. So if I go back and I look at my formulas right here, the first one is y is equal 1,000 times 1.005 to the 4x power. 1.005. So I can remember that. So this is going to do a formula in Excel or Google Sheets. You just hit equals, and it's going to be $1,000 And then multiplication is this little star. It's on shift 8. So that's 1,000 times, and then 1.005. And then to raise it to a power, I'm going to hit shift and the number 6. So that's to the power of, and then it's like, okay, this box right here is the power. So how do I get that? I just click it. And it didn't work. Okay, let me have a second go at that. Let me delete this. And I'm also going to make this column a little bit bigger. Let me try this again. So this equals $1,000. Whoops, $1,000 times 1.005 raised to the power of, it's that one, raised to the power of A2. So what that means is A2 is the value that's stored in that box, right? So whatever number this is, if it's the number 1, now I'm raising it to the first power. But by leaving it as a 0, all these numbers are going to be visible here. Now that formula is typed, you can see it's right up here, 1,000 times 1.005 raised to the A2 power. I can drag it down to the next box. And what's cool is you can see it automatically updates. So now instead of saying to the A2 power, it says to the A3 power. So both Excel and what's it called, Sheets, they know that they have this idea that it's a relationship. So it's saying, look, I want you to raise it to the power of the number stored immediately to, I guess it would be its right or our left, to the left of this cell. So it just goes and gets that number, and that's the power. So what's cool about it is now I can just drag this down, and as soon as I release the mouse, it automatically calculates all those values, right? So now I can see what this option 1 is worth for the 5th year, and if I scroll down further, it'll give me the 25th year. So same thing here. I'm going to do the same thing for option 2, but our formula is a little bit different. Let's remind ourselves what the formula is for option 2. For option 2, it's y equals 1,000 times 1.00125, and then we're raising, oh, I forgot to raise it to the 4x, didn't I? Yeah, I think I just raised it to the x. I got to raise it to the 4x. Let's go back and change. Ooh, good thing I caught that. So there's a problem with this formula. This is supposed to be raised to the, and I'm going to open parentheses 4, and then times the A2, and then I'm going to close parens. Okay, that does not change. That does not change year 0 at all, right? Because to the 0, 4 times 0 is still 0, but it's going to change all the other years. So you can see this formula, I updated this box. The formula is now this one. If I come down here, it's the same old formula. So what I'm going to do is grab this, and I'm going to drag this new formula down. And when I release it, it automatically, in like 1 second or less than a second, updates all of them. So that's better, because at year 5 now I'm 104, roughly $105. Okay, so now I think I forgot the number for the other one. So it's times 1.00125. All right, so we're going to go 1. So this equals $1,000 times, open parentheses, 1.00125 raised to the power of, and I'm going to go 12 times, and then I'm going to go get the year number. So raised times 12 to the number of years, and this should give me $1,000. All right. So you can see the two different formulas are right here. 1,000 times 1.005. This is 1,000 times 1.00125 to the 12x, essentially. And then I just grab this again. I'm going to copy this all the way down to here. Doop. Interesting. What did I must have the wrong multiplier here. Maybe not. Okay, this is looking right. So if I'm just going to keep it in the account for 5 years, option 1 is better, right? Option 1 puts me at $1,105. Now, if I'm going to go down to the 25 years, at 25 years, it looks like option one is still better. So even though I've got more compounding periods, that interest rate was so low that it didn't get out ahead of it. Wow, I wonder how far I'd have to go before option two actually looked better. Well, it's funny that you asked that. So if I take all three of these are all based on formulas. So I can drag these down, and I'm just holding this and I'm just dragging 200, 300, da 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 da. Da. Okay. 1 2 1 2 1 2 1 1 2 1 2 1 2. Wow, option. I've either done something wrong with option two, or it's disappointing me. I always believe in the power of compounding more often, but it's just not 1.00125, 1.00125, and then 12x. Huh. 00125. Yeah. 005. And that's 4 times the x, and that's 12 times the x. All right, well, there we have it. Option A works for both 5 years and for 12 years.